In this video, I'll be ranking 10 theories of everything, which attempt to explain the fundamental nature of our universe. Of course, there are many more toes out there. I've chosen to rank these based on a combination of expert opinion, copious research, and, ultimately, my intuition. Kicking off at number 10 with geometric unity, which aims to unify Einstein's GR, Yang-Mills theory, and Dirac's theory of fermions from a single, yet-to-be-discovered geometric principle. Along with my number 8 pick, geometric unity gets tied up with its controversial creator. By examining the geometric properties of curvature and torsion, Eric Weinstein hopes to reveal deeper connections between gravity, gauge fields, and matter. GU, or GA, is highly speculative and supported by few physicists. Mathematical physicist Timothy Witten says it has gaps, both mathematical and physical in origin, that jeopardize geometric unity as a well-defined theory, much less one that is a candidate for a theory of everything. To its credit, GU stimulates new ways of thinking about fundamental physics, and there's broad potential in geometric concepts unifying GR and quantum mechanics. Take, for example, Nima Arkani Hamed's amplituhedron. Weinstein is prone to overhype. He once called the Hopf vibration the most important object in the universe, only to never mention it again. While I doubt its importance, my explainer on it is my most popular video, making it a significant object in my universe. Eric does emphasize the observer's role as integral to the fabric of reality. So GU, in one word, his word, observerse. On to number 9. E8. E8 theory uses the complex structure of the largest exceptional Lie group to unify all fundamental forces as vibrating particles in this mathematical space. E8 is a complex, 8-dimensional mathematical shape with 248 points. The idea is that all the fundamental forces, like gravity and electromagnetism, and particles, like electrons and quarks, can be described as different parts of this beautiful E8 shape. Surfer physicist Garrett Lisi simplifies the universe into one elegant structure where connections on E8 match up to real-world interactions and certain symmetries in physics. Unfortunately, this exceptionally simple theory of everything relies on an as-yet undiscovered 24 particles more than we've confirmed with the standard model. Along with all toes, E8 lacks experimental confirmation. Critics argue it oversimplifies complex physical phenomena. For me, E8 is more appealing and concrete than many toes. It gets bonus points for producing the 4 familiar dimensions of our physical universe. And physicist Tony Smith at Quantum Gravity Research has even found a connection between E8 and Jung's Red Book. Either Lisi has discovered some remarkable coincidences, or there's something more substantial here. I believe in the dude living in a van down by the beach. In one word, swell. Quick joke before we move on. Why was MC squared afraid? Because E8, 9. If you were previously enjoying this video, please subscribe to the channel. On to number 8. CTMU. The cognitive theoretic model of the universe integrates ideas from philosophy, math, and cognitive science to propose reality as a programming language. Many people, understandably, write off the CTMU as gobbledygook. I found it to be largely intractable myself. It's highly abstract and, as far as I know, lacking any empirical support. Chris Langan attempts to integrate several concepts I consider significant, ranging from John Wheeler's self-excited circuit universe to Claude Shannon's communication theory. He incorporates homology, the idea that each part of reality reflects the whole, resulting in a fractal structure of the universe. In his own words, the CTMU describes reality as a self-configuring, self-processing language, or SCSPL, a reflexive intrinsic language characterized by self-reference and recursive self-definition. Verbose, yes, but I could get on board with a fractal, computational, linguistic view of reality. Terence McKenna often commented on the syntactical nature of reality, saying, "The world is made of language." The CTMU lacks formalism or testability, but I think Langan might be in the right zip code. In one word, syntax. On to number 7. Twistor theory. Twistor theory proposes a new way of tying quantum mechanics and space-time using complex geometric shapes called twistors. In T2, instead of describing the positions of objects in space and time directly, we use twistors. Think of twistors as a new way of keeping track of where things are and how they're moving, but in a more abstract, simpler form. It replaces traditional space-time coordinates with twistors to simplify the connections of light rays and particle interactions. In the twistor approach, space-time is secondary, with events being derived objects that correspond to compact holomorphic curves in a complex threefold, the twistor space. By using twistors, some complicated problems in physics, especially those involving space, time, and the movement of light, become easier to solve. While powerful, twistor theory's applications are more limited and not as broad as some other theories. Roger Penrose is the only Nobel laureate on this top 10 list, purporting other strong theories like conformal cyclic cosmology and orchestrated objective reduction. Twistor theory, in one word, holomorphic. Quantum error correction. As applied here, QEC asserts spacetime is a quantum error-correcting code which protects information from noise and decoherence. This one stretches the definition of theory of everything, though it can be seen as a stepping stone towards one. One of the key aspects addressed by QEC is the holographic principle, the strange but proven fact that all of the information contained in a volume of space can be encoded on its boundary in lower dimensions. In particular, the ADS-CFT correspondence provides a duality between a gravitational theory in a higher dimensional ADS space and a quantum field theory on its lower dimensional boundary. Physicists Ahmed Almheiri, Shi Dong, and Daniel Harlow have proposed that the way information is encoded in this duality resembles the way quantum error-correcting codes preserve information. Just as a quantum error-correcting code can spread information across many qubits to protect it from local errors, the information in a gravitational theory can be distributed across the boundary of ADS space, making it robust against perturbations. Relatedly, physicist James Gates has found error-checking codes within the equations of supersymmetry, specifically doubly even self-dual linear binary error-correcting block codes. QEC offers a new way to describe black holes as the breakdown of correctability. When errors become too numerous to track in the fabric of spacetime, a black hole forms, acting like a sink for an observer's ignorance. The concepts of holography and error correction offer insights that transcend specific physical domains, suggesting broader applications. I'm reminded of Carl Friston's free energy principle, which could be boiled down to error-correcting predictions. Maybe we're ultimately just beta testers in a game. I have to mention there's a topological flavor to QEC as well, best tied to physicist John Preskill. If you want to dive deeper into these topics, check out my explainer video at the end of this video. In one word, cryptographic. On to number 5. Causal dynamical triangulation. Causal dynamical triangulation utilizes a path integral approach by discretizing spacetime as a series of transforming triangles. Instead of smooth and continuous, CDT models spacetime using tiny, evolving, triangle-shaped pieces, called simplexes. Physicist Renate Loll runs Monte Carlo simulations approximating fundamental quantum reality as tiny polygonal shapes that spontaneously self-assemble into larger patches of spacetime. These simplices aren't just randomly placed. They're arranged in a specific way that follows rules about how they can connect and how many edges they can share with other triangles in order to produce any desired curvature. CDT offers a discrete computational approach to spacetime. CDT is quite appealing because it depends on little background structure, few assumptions, and few free parameters. Ingredients or priors are near a bare minimum. Loll claims CDT is currently the only candidate theory of gravity which can dynamically generate a spacetime with semi-classical properties from pure quantum excitations without using a background metric. When constructing spacetime using triangles, CDT arranges them in a manner that preserves the ordering of events according to causality. This respects the maximum speed limit of information transfer, which is the speed of light. As with many theories of quantum gravity, experimental validation is challenging and remains a future goal. But CDT is so promising because the best way to understand something is to build it yourself. Loll is literally simulating universes in her computer. In one word, simplex. On to number 4. Fusions of consciousness. Fusions claims consciousness itself is fundamental reality, and our sentience generates the universe. Cognitive scientist Donald Hoffman is not the first to propose this panpsychist idea. Notable figures like Whitehead, Chalmers, Spira, Nagel, Goff, and Kastrup have supported a Huxleyan mind-at-large idea. Once disregarded, panpsychism has seen a resurgence in recent years, and Hoffman takes, to my knowledge, the most concrete approach. The vast majority of scientists believe consciousness is a bottom-up, materialistic phenomenon. Through some neuronal integration in the brain, consciousness emerges. Hoffman flips this idea on its head, claiming that sentience itself is fundamental, and the world as we experience it emerges from consciousness. He proposes that only experiences and probabilistic relationships are fundamental. He sets forth a mathematical theory of conscious agents whose dynamics are described by Markov chains. These conscious agents interact, mapping to 2 levels. First, through decorated permutations, then through the amplituhedron, to project into particles in spacetime. Spacetime and scattering processes are a data structure that codes for interactions of conscious agents. We shouldn't take it lightly that we all awaken in media res. Our everyday frame of reference, moment-to-moment existence itself, is beyond doubt. Consciousness is the only game in town, and mystical, altered state experiences lend credence to panpsychism. As is alluded to by fusions, maybe we are approaching an omega point. There are still evidential gaps, but I appreciate Hoffman's daring, unconventional approach here. I'm a huge fan of his work, and you can watch my exhaustive interview with him about fusions of consciousness at the end of this video. In one word, experiential. On to number 3. String/M theory. String theory proposes all particles are tiny vibrating strings, offering a single framework for all quantum excitations and fundamental forces. The different particles we observe correspond to different vibrational modes of these strings, which can be open, with 2 ends, or closed, forming loops. Just as a single violin string can produce many notes, a fundamental string can vibrate in various ways, each corresponding to a unique particle with specific properties such as mass and charge. Initially, there were 5 distinct string theories, each with slight variations. Ed Witten unified these as facets of a single, deeper theory. M theory operates in 11 dimensions, 10 spatial and 1 temporal, including not only strings but also higher dimensional objects called branes, short for membranes. These branes have various dimensions, like 2D, 2 branes, or 3D, 3 branes. The extra dimensions are compactified, meaning they are curled up so small that they are not observable at everyday scales. M theory introduces dualities, mathematical relationships which reveal that seemingly incompatible physical theories are actually equivalent descriptions of the same phenomena. These dualities connect the different string theories and M theory. For example, type 2A and type 2B string theories are related through T-duality, and strong-weak coupling duality, S-duality, relates strong and weak interaction strengths. One of the remarkable insights from M-theory is the gauge-gravity duality, or ADS-CFT correspondence. This duality posits that a gravity theory in a higher dimensional ADS space is equivalent to a gauge theory, like quantum field theory, on the lower dimensional boundary of that space. D-branes can host gauge theories on their surfaces. This duality has greatly advanced our understanding of quantum gravity. Despite its mathematical elegance, there's no direct experimental evidence for string theory or M-theory due to the required energy scales beyond our current capabilities. Part of the rank reasoning is string theory seems past its prime. It hasn't met expectations. Though unlike most TOEs, M-theory has been successful in incorporating all fundamental forces, including gravity, into a single framework. Check out Curt Jaimungal's excellent string theory explainer video for more details. If you picked a random day in the past 30 years and were asked what the best TOE was, you could easily say string or M-theory. Will any answers emerge from the swampland? In one word, compactified. On to number 2. Computational universe. The Wolfram physics project proposes the universe is a vast computational system governed by simple rules, with hypergraphs as the underlying structure. Instead of equations and particles being the fundamental building blocks, Stephen Wolfram believes that simple instructions operating on discrete elements, like bits in a computer, could underlie all physical phenomena. Wolfram utilizes hypergraphs to model these interactions. A hypergraph consists of vertices, i.e. nodes, and hyperedges. Hyperedges connect sets of vertices rather than pairs, allowing for more complex relationships. In his view, these computational constraints generate sophisticated behaviors and deterministic structures, including the laws of physics and the emergence of space, time, and matter. Wolfram has explored cellular automata extensively as a model for these computational rules. Cellular automata are basic programs where discrete cells evolve through the iterative application of rules based on the states of neighboring cells. Simple local interactions can lead to complex global behaviors. The emphasis here on information transfer is paramount. Wolfram's Ruliad encompasses every conceivable computational outcome by applying every possible rule iteratively. Anchored by the principle of computational equivalence, it highlights the roles of information processing and algorithmic complexity in shaping physical reality. While Wolfram's theory offers a novel perspective, it remains speculative with limited acceptance in the scientific community. Practical applications are yet to be demonstrated, raising questions about its feasibility and scope. It's early days, but I highly respect the approach. As Richard Feynman once said, "What I cannot build, I do not understand." We should explore the Ruliad. Computational irreducibility looks tethered to time. If you had to bet on an architect for a new kind of universe, who better than Stephen Wolfram? In one word, algorithmic. On to number 1. Loop quantum gravity. LQG aims to unify gravity with quantum mechanics by quantizing spacetime itself, envisioning space as a fabric woven from tiny discrete loops. Quantized means that something is divided into small discrete units rather than being continuous. Imagine you have a staircase and a ramp. The ramp represents a continuous surface where you can stand anywhere you like, while the staircase represents a quantized surface where you can only stand on the steps, not in between them. LQG posits that space is made up of tiny discrete chunks called quantum loops or spin networks. These are like the building blocks of space, similar to how atoms are the building blocks of matter. They are graphs with edges labeled by quantum numbers, i.e. spins. Unlike some theories, LQG does not assume spacetime exists independently. Instead, it emerges from the network of interconnected quantum loops. Space is not smooth and continuous. The geometry of space is defined by how these quantum loops are linked together. These loops, representing quantized areas and volumes, interact and evolve over discrete steps. The loops can alter their connections, creating different shapes and structures of space at minuscule scales. They form a network that can change and reconfigure itself dynamically. This structure at the Planck scale is crucial for understanding phenomena where quantum effects dominate, such as near black holes or in the early universe. In LQG, spacetime is quantized into tiny units or quanta. This prevents the mathematical singularities that arise in classical general relativity, where infinities appear in equations describing the curvature of spacetime at certain points, like at the Big Bang or at the center of a black hole. Instead, the interior of a black hole by LQG is described by a quantum bounce, where spacetime curvature becomes finite and well-behaved. Loop quantum cosmology, a branch of LQG, applies its principles to the early universe. In LQC, the Big Bang singularity is replaced by a quantum phase preceding the universe's expansion from a highly dense state, leading to a big bounce that avoids the classical singularity problem. Similarly, LQG proposes that time is quantized, meaning it advances in discrete steps rather than as a continuous flow. Time is not an absolute backdrop against which events occur, but rather a measure of change that depends on the interactions between systems. Rovelli's ideas, rooted in statistical mechanics, suggest that macroscopic properties like the flow of time emerge from the collective behavior of countless microscopic components. Increasing entropy is a statistical effect of the system moving towards more probable, more disordered states. As Rovelli writes, time is ignorance. There are still some challenges connecting LQG with the other fundamental forces, but it gets bonus points for not requiring extra dimensions. And LQC's resolution of singularities has led to specific predictions and insights, such as modifications to black hole thermodynamics and the universe's evolution at extremely high energies. These predictions are distinct from classical GR and, above other toes, offer potential tests through observations or experimental data in the future. In one word, holonomic. Before we depart, a few parting shots. First, if you got this far, thank you so much for watching, and please subscribe to the channel. Next, aside from QEC at number 6, I only highlighted one figurehead for each toe. It should be noted that in most cases, entire teams of brilliant minds are working on each theory. Shout out to all of them. After making this video, there's two specific things I can't quite shake. First, on 2 occasions, with quantum error correction and loop quantum gravity, the concept of ignorance is tied to black holes and time, respectively. I think there is a deep connection here with Shannon information theory, which I'll have to cover in a future video. Second, I hope you enjoyed my attempt to distill each toe into a single word. It was a fun exercise aided by ChatGPT and powerthesaurus.org, and I was surprised that for most toes, the prefix holo, H-O-L-O, kept popping up. For 6 of the 10, a term with holo could reasonably be used. Maybe this isn't that astounding, given we're covering toes here, and the Greek prefix holo means whole or entire. But when I see a pattern like this, it makes me want to learn more about holomorphic transformations and holonomic curvature. I've long loved the concept of holons, too. Watch this space. Finally, most likely, we are nowhere close to an accurate theory of everything. Unifying quantum gravity with general relativity is hard enough, but most toes don't explain dark matter or dark energy, which together make up 95% of the mass in the universe. Few toes adequately address the concepts of time, entropy, black holes, and singularities, not to mention creation itself. We're still deep in Plato's cave. The only difference now is we're calling shadows holographic projections. Thank you for watching.